Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. In today's video we want to have another look at polynumbers as a replacement for polynomials and just reinforce the formal approaches to the derivative and the integral that we've already talked about for such polynumbers. So in traditional calculus courses we have polynomials. Things like p of x equals 3 minus x plus 2x cubed. And this is often thought of as a function that inputs some number x and outputs this number here. And there's a little bit of a ambiguity or imprecision as to the role of the x here. At some level, x is a number or standing for a number, but sometimes we think of x as a variable, whatever a variable is. And it's a little bit challenging actually to pin down what variables are and to distinguish between independent and dependent variables and so on. So what we do is we try to replace this framework, familiar, traditional though it is, of polynomials with this somewhat more modern data theoretic point of view. Polynumbers. So we encode this kind of object rather just by the list of coefficients, and we think of this list as being essentially primary. This is really what the object is. So instead of writing this, we would write p equals 3 minus 1, 0, 2. These are obviously the coefficients that are appearing up here. But when we write it this way, there's no more sign of an x or a y or any other variable. It's just p equals this list of numbers, and we write it vertically like this, at least at first. And I like to put this little bracket on top to distinguish it from other kinds of lists, and also to allow us this idea that there's a bit of flexibility in terms of adding zeros at the end. So if we take the same thing here, we could, first of all, rewrite it like this. This is maybe a little bit more friendly for LaTeX, okay? So we might use this kind of notation when we're typing something up with a left bar here and an overline there. And then this polynumber here will agree is the same as this polynumber here, where we've just added a zero or maybe a couple of zeros to the end. So that's our basic agreement that there's an ambiguity or flexibility in terms of adding additional zeros at the end of the polynumber below it. Okay, so there's just a list of numbers, that's all we have, and there's no associated variable as there is in the polynomial story. And these are the fundamental objects that actually we end up doing a lot of calculus with, a lot of algebra too. So let's review how the familiar operations of polynomial arithmetic translate over to the polynumber setting. So operation of addition is just component-wise. Here's a polynumber, here's another polynumber. We add them component-wise. 2 plus 0 is 2, 1 plus minus 5 is minus 4, 4 plus 2 is 6. And here there's nothing, and so we regard that as like 0. So 0 plus 3 is 3. Or we can also take the difference to get that one there. Scalar multiplication, we're allowed to multiply a polynumber by a scalar, in other words a number, so 5 times 214 will be 10, 5, 20. We just multiply each of the entries by the scalar. More interesting, of course, is multiplication, and here we use something called the Cauchy product sometimes. So what we do is, here's a polynumber 214, here's another one 0, minus 5, 2, 3. So the 0th element in the product is the product of the 0th elements here. So this is sort of level 0, level 0. 2 times 0, that's 0. That's what we get there. The level 1 entry in the product is the product of the 0 level here times the 1 level here, 2 times minus 5, plus the 1 level here entry times the 0 entry there. 1 times 0, 0 times 1. So a total of minus 10. The 2 entry is the 0th one times the 2 level entry, 2 times 2, plus the 1 times minus 5, plus the 4 times 0. So what we're doing is we're taking products of entries so that the sum of the indices is the index that we're obtaining. So here's the index 2 that we're interested in. So we take 0 and 2, 1 and 1, and 2 and 0. All the combinations that sum to 2. We take the products and then add all those products. So for example, for the next one, the 3 entry, we would take all possible products of elements here and elements here for which the corresponding indices sum to 3. So the 0th one and the 3rd one, that's 2 times 3. The first one times the second one, that's 1 times 2. The third one times the first one, that's 4 times minus 5. Also the 4th one times the 0th one, but that's going to be 0. So that's not going to contribute. Get minus 12. But it keeps on going, so then the 4th one would be the 0 times the 4th one, but there isn't a 4th one. But there is a 1 and a 3 here. Level 1, level 3. And there's also a level 2 times level 2 that also contributes. And finally, there is a level 5, which is the level 2, 1 times level 3, 1. 4 times 3 is 12. Now, to make the arithmetic more manageable and to connect it a little bit more directly with the usual polynomial story, it's useful to introduce some special polynumbers. In particular, this one called alpha. That's going to be the most important one aside from the number 1. So alpha is the polynumber 0, 1. And its square then will be 0, 0, 1. And its cube will be 0, 0, 0, 1, and so on. In general, the element alpha to the k will be the polynumber that has a single 1 in the kth position, where, as always, we start with the 0th position, and then the 1st position, and so on. So, for example, this polynumber here, p equals 3 minus 1, 0, 2, can now be written as a sum of powers of alpha. It's 3 times alpha to the 0, which by agreement is just the polynumber 1, with a single 1 there and nothing else, minus 1 times alpha to the 1, or alpha, plus 0 alpha squared, plus 2 alpha cubed. And we'll agree to write alpha to the 0 just as 1, so we'll just write 3. And we'll agree to write alpha to the 1 just as alpha. So we get something that looks like a familiar polynomial, but it's now a polynomial in alpha. But crucially, alpha is not a variable. Okay? It's not something outside the world of polynumbers. It actually is a particular polynumber, namely that one right there. So this is just a shorthand for representing polynumbers, sort of an internal shorthand. Doesn't require any knowledge of variables coming from outside. So now we can write a general polynumber as a combination of powers of alpha, say a0 plus a1 alpha plus a2 alpha squared, and so on up to a sub k alpha to the k. And if this alpha sub k here, this coefficient, is non-zero, so that's the highest non-zero power of alpha that appears, then we'll say that the degree of this polynumber is k. It's its degree. And just emphasizing that alpha is not a variable, it's just a very special polynumber. Okay, so now let's look at evaluation of a polynumber. So if p is this polynumber here, a0 plus a1 alpha all the way up to a k alpha to the k, and c is a number, which for us usually means a rational number, then we will define p of c, the evaluation of p at c, to be this number here, a0 plus a1 times c plus a2 times c squared, and so on up to ak times c to the k. So in other words, we take the expression for p in terms of alpha and we replace each of the alphas with c. So we get an expression involving sums of powers of c. And that's a number. It's the evaluation of p at c. So this is how we recover the polynomial as a function kind of story. That given a polynumber, we can then evaluate it at a number, and we get another number. But intrinsically, the polynumber itself is not a function. It's just an object. Now there's a kind of generalization or extension of this where we look at the same formula, but we apply it not to a number, but to another polynumber. Polynumbers are like generalizations of numbers. Okay, so that's a polynumber. If we stripped off all the terms involving alpha powers of alpha, then we would just have a single number. So numbers are like very special cases of polynumbers. The simplest kinds where there's just a single entry at the very top in the 0th level and nothing else below it. So we're extending our arithmetic of numbers to a more general framework. That's how I want you to think about it. That will be very important later on for us. So what we're doing now is we're saying, okay, we've just defined this for a number c. Let's extend it so that c is now possibly a polynumber, namely q. In that case, we can define a new object, p of q, okay, which is going to be the same kind of thing, but now we have an expression a0 plus a1q plus a2q squared all the way up to a sub k q to the k. What we get when we replace the alpha in the expression for p with the polynumber q. So this is p of q. And we're going to introduce a new, well, not really new, but I mean familiar composition notation, p with a little circle q. So p little circle q is p of q. It's this expression here. And what is this? This is another polynumber. Because q is a polynumber, powers of q, they're also polynumbers. So we got a linear combination of polynumbers, that's another polynumber. So ultimately this is another list of numbers if we actually wrote it down officially. Okay, so there's various properties that are satisfied with the arithmetic. For example, the sum of two polynumbers p plus q. If we evaluate that at a number c, that's the same as p of c plus q of c. If we evaluate the product p times q at c, then we get the product of p of c times q of c. And when we evaluate the composition p circle q at c, we get p of q of c. So these are all kind of simple things, but one has to check them just to make sure that this agrees with the usual yoga of polynomials, except now everything is in the world of polynumbers. Okay, so now let's talk about the derivative and the integral in the context of the world of polynumbers. And we're talking about the Faulhaber derivative and integral. So these are these purely algebraic operations that Faulhaber introduced in the context of his search for expressions for sums of powers. Okay? And at least at first, they don't necessarily have much to do with the usual idea of derivative as a slope of a tangent or integral as an area under a curve. Okay? It's a purely formal algebraic thing. And we can now state that purely in terms of the framework of polynumbers. So if p is this polynumber, a0 plus a1 alpha plus a2 alpha squared all the way up to a sub k alpha to the k, then here is the definition of the derivative. It's a definition. We might as well make that explicit. We'll put 3 bars there and here also for the integral. All right, so this is the capital D derivative. So when we talk about it, I'll put a capital D for the derivative. So this is the derivative of p. What is it? It's another polynumber obtained from this one by, well, essentially using this rule. So it's a1 plus 2a2 alpha plus 3a3 alpha squared all the way up to k a sub k alpha to the k minus 1. So the guiding rule here, there's really only one rule, which is that the derivative of alpha to the n is n times alpha to the n minus 1. So the power comes down as a coefficient, and then the new power is 1 reduced. So this term here, its derivative will be 2 times a2 times alpha to the 1. Just that one there. The derivative here is k times a sub k times alpha to the k minus 1. The same rule. So notably, what happens to this term here? Well, this a0 is really a0 times alpha to the 0. So if you apply the same rule, if there's a 0 here, that 0 coming down will mean that we multiply everything by 0, so we get 0. That's why this term sort of drops off and we don't get it. Okay, now the inverse operation, again purely at a formal level, is the S operation, capital S operation, which we're going to call the integral of p. And S of p is the same as there, it's a0 times alpha plus a1 alpha squared over 2 plus a2 alpha cubed over 3 all the way up to a sub k alpha to the k plus 1 over k plus 1. It's the inverse operation of this in some reasonable fashion. So we're raising the exponent. So for example, for this one here, instead of dropping the exponent, we're raising the exponent, so it becomes a2 alpha cubed. Instead of multiplying by the coefficient, we're dividing by it. And there's the simple rule corresponding to this one, that S of alpha to the n is alpha to the n plus 1 over n plus 1. And here, n are always natural numbers, 0, 1, 2, 3, and so on. All right, so these two basic rules, when extended to polynumbers linearly, define for us the capital D derivative and the capital S integral of a polynumber. It's purely in the world of polynumbers. We're not taking the derivative with respect to a variable, okay? We're just taking the derivative. We're not integrating with respect to a variable, we're just integrating. Okay, so it's a difference. It's a slightly unfamiliar situation if you're used to calculus. If you're used to calculus, you're used to differentiating with respect to x or with respect to y or integrating with respect to x or z or something or other. We're not doing that here. It's purely formal. You take a polynumber, which is a list of numbers, you differentiate it, you get another list of numbers, or you integrate it, you get another list of numbers. End of story. All right, so our formal Faulhaber derivative and Faulhaber integral obey some pleasant properties. First of all, they're linear. So d of p plus q is d of p plus d of q, and d of lambda times p is lambda times d of p, where lambda is a number. And same thing for the integral. S of p plus q is s of p plus s of q, and s of lambda times p is lambda times s of p. And importantly, there's a derivative integral composition theorem. We've already seen this. Here's a polynumber p. Then this first one says that if you integrate p and then you differentiate, what you get back is p. So d of s of p equals p. And this one is almost the same, but if we do it in a different order, we almost get p back, but not quite. So if we take p and we differentiate it first and then integrate it, we get p minus a0. In other words, we get back the same polynumber that we started with, except that the constant term is gone. The reason it's gone is because when we differentiate it, it is killed. It's multiplied by 0, so it's gone. So integrating it is not going to bring it back to life. Okay, so these operations are almost inverses, but we do have to be careful that they're not entirely inverses. That makes a big difference in calculus. All right, so now there are two important rules that we've actually already seen before in the problems for the course in an earlier chapter. But let me remind you what they are in this context of polynumbers. So we're wanting to frame things in terms of polynumbers more than in terms of polynomials. So the product rule, if p and q are polynumbers, then the derivative of the product p times q is the derivative of p times q plus p times the derivative of q. And the chain rule tells you how to take the derivative of the composition. So if p and q are polynumbers, then the derivative of p circle q, the composition of p and q, is this thing times this thing. So the first thing here is the derivative of p circle q. So the composition of the derivative of p with q. And then we have to multiply that polynumber by another one, which is just the derivative of q. So the derivative of p and the derivative of q are both appearing, but because this is not really symmetrical, right? P circle q is not the same as q circle p. They're appearing here in different ways. So we take this expression, we replace the p with d of p, and then to compensate, we multiply by d of q. And these rules can be established purely algebraically, and we talked about that in the work problems in the earlier chapter. So make sure you go back and check that out. Okay, so these are purely algebraic results that just are consequences of the algebra of polynumbers. So let's illustrate, first of all, the product rule. So here's a polynumber p. It's alpha plus 2 alpha squared. Here's another one, q, which is 1 minus alpha cubed. So if we take the derivative of the product, what are we going to get? So the product is alpha plus 2 alpha squared minus alpha to the fourth minus 2 alpha to the fifth. So there's the product there. We differentiate it. The derivative of alpha is 1. The derivative of 2 alpha squared is 4 alpha. The derivative of minus alpha to the fourth is minus 4 alpha cubed. And the derivative of minus 2 alpha to the fifth is minus 10 alpha to the fourth. Okay, and the product rule says that this ought to be the same as the derivative of p. There's p. There's its derivative. 1 plus 4 alpha. There's the derivative of p. Times q. There's times q. Plus p. There's p. Times the derivative of q. The derivative of q is minus 3 alpha squared. So the claim is when you expand this out, you get exactly this. And I'll leave it to you to check if that's actually true. That's an illustration of the product rule on polynumbers. And here's an example of the chain rule, taking the derivative of a composition. So we'll use the same p, alpha plus 2 alpha squared, the same q, which is 1 minus alpha cubed. So if we look at the composition p circle q, what is that? Well, it means that we're replacing the alpha in p with q. So this is the polynumber q plus 2q squared. And that's then there's q plus 2q squared. We expand this out and we get 3, it's constant. And how many alpha cubes? There's minus alpha cubed there. There'll be minus 4 alpha cubed here, so minus 5 alpha cubed altogether. And then also plus the alpha to the 6 that appears here times 2. Okay, so let's look at the derivative of the composition. The derivative of this is, the derivative of 3 is 0. The derivative of this is minus 15 times alpha squared. The derivative here is 6 times 2 is 12 alpha to the 5. Now, the other side of the chain rule has d of p circle q, and it also has d of q. So let's look at those individually. So d of p circle q, we need the derivative of p, there it is there, 1 plus 4 alpha, circle q. That means we're replacing the alpha here with q. So that's 1 plus 4 times, there's the q, 1 minus alpha cubed. So that as a polynumber is 5 minus 4 alpha cubed. And the other ingredient is the derivative of q. There's q, its derivative is minus 3 alpha squared. So the other side of the chain rule is the product of derivative of p circle q with the derivative of q. So it's the product of this thing that we calculated there times this thing we calculated there. You do the product, you get minus 15 alpha squared plus 12 alpha to the fifth, which is the same thing that we got up here. So the derivative of the composition is the derivative of p circle q times the derivative of q. That's the chain rule for derivatives of compositions. Okay, so this has been a little bit of a reminder and also to reinforce the idea that we want to gently but surely move from polynomials to polynumbers. Okay? And another thing that we're kind of doing more and more is when we write our polynumbers, we like to write them in terms of increasing powers of alpha. We like to start with the constant term, and then the linear term, and then the quadratic term, and so on. Corresponding how we read it as a vertical column, starting with the 0th element, and then the first element, and the second element, and so on. So that's often not what we do when we work with polynomials. Often we introduce the highest power first, but we'll try to make a little bit of a shift and gently start ordering our polynomials or polynumbers in terms of increasing powers of alpha rather than decreasing powers of alpha. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.